Excellent.
Go ahead. Thank you.
So first, thanks to Susanna and Juliana for inviting me to give this talk. And this is, I mean, all I'm saying here is really joint work with lots of people who participated in the competition, who helped me organize the competition, who helped establish the standards, the formats that the competition is based on, and so on. And as it is basically focusing on the one competition on quantitative things that we set up, but I'll try, of course, to be a bit general. What are the challenges once you do competitions for stochastic, well, essentially stochastic models here, sometimes with a bit of timing in them. So, yeah, I would say let's delve right into that. I'm feeling a bit guilty to have 30 minutes where everybody else got only 10 minutes, but on the other hand, in some sense, I'll be presenting 9 tools here, so I hope that's okay. So, as I said, general challenges, but also the one competition that we set up in essence 2 or 3 years ago called QComp on quantitative analysis. We try to be very general there, not necessarily say quantitative verification, quantitative model checking, but to try to include any kind of solution methods for the kinds of models we're dealing with. So, well, first of all, I mean, as a quantitative thing, we are somewhere in this space of fundamental formalisms that I would say, from discrete and continuous time Markov chains up to stochastic hybrid automata or stochastic hybrid systems, if you want. And then, of course, there's lots of levels in between where you can combine timing with probabilities, but not with differential equations and so on. And first of all, when we set this up, of course, inspired by, as you mentioned, all the competitions that are going on in other fields, we looked at a bunch of them, and we first established, okay, we want a friendly setup here. I mean, there are really tough competitions. I think the SAT competition, also as VComp, is a bit, you really get a ranking and a winner. And we didn't really want that because we're all friends and we don't want to stop being friends over a competition among most of the participants. So that was the first step. That also allowed us to do a lot of arrangements that you can't really do if you're really hard competing. Then, so we could say, okay, we just agree, we have a problem here. We need to say what precision the algorithm internally uses, and you can gain some performance if you do it differently, but we all agreed to just use a certain parameter. And then we had to figure out, well, what part of this space to compete on, right? I mean, the most important thing is that you have some agreement on the kinds of models, on the kinds of formalisms you work with, and then looking at what the tools that we are aware of can do, and also the tools that expressed interest in the competition. We, in essence, then focused on Markov chains, Markov decision processes with exponential distributions, and probabilistic timed automata, because in essence you can analyze them by going back to Markov decision processes. And so these are more the mathematical formalisms, but then of course you need to write your models in some form. And the models that we used in the end came from a wide variety of languages. So we had Petri nets in formats supported by Great SPN, is in essence because Storm could convert them to other formats. We had planning problems. We had the Prism language, which we saw variants of today. But most importantly, all of these models that we had in various languages were also then available in our Jani kind of model exchange standard. This is a JSON-based format that we developed a few years ago with the intentional purpose to allow the exchange of models between tools. You don't want to write them by hand, but there's a Storm, for example, can convert lots of formalisms into the Jani format. And in that way, you don't really need support for all of these models if you want to take part in the competition, as long as you have support for the Jani format. And I think that's very important for the competition, but that's also an outcome of such a competition, that you drive a bit of standardization among a bunch of tools. You can't really drive the well-established ones, but all the newcomers then can at least work on this. So we also had to decide what kinds of properties you want to check, what kinds of numbers you want to compute, and we just decided to use the very, very basic stochastic properties. So probability of reaching a goal, expected reward to reach it, and steady state probabilities, and then invariance, where you can have a time-bounded probabilistic reachability question and stuff like that, where it makes sense. And we took then benchmarks from a related initiative, which was that we set up a benchmark set, which is online at this URL, of some, I think, around 80 different models. Each of them is kind of parameterized so that you can scale them up or down. And in particular, each of them is available with a Jani version. And then we, in essence, asked everyone to propose their favorite models, where probably their tool does well on. But since we had a bunch of participants, we hope that this gave a nice balance of different benchmarks. So this is the fundamental setup at the beginning that we agreed on. And I want to quickly go over to a bit of the challenges that come specific to the stochastic or quantitative setting. So for that, I've prepared some slides on which kinds of algorithms did we actually get in the tools in here. So we had a bit of a call for tools among the people we knew, who we asked to ask other people they knew, to try to get everyone in who could possibly be in. For some reason, we didn't really manage to get many PetriNet-based tools or any at all, which we were a bit sad about in the end, but maybe you can tell me if you want to participate next time. Now here I have a few slides on probabilistic model checking, statistical model checking and stuff, but I can really go fast, I think, because especially Carlos and Benoit gave us very good introductions. So I mean, probabilistic model checking is what I call the numeric analytic, whatever you want, a solution where you build the state space and then you run some algorithm on it that gives you a more or less precise solution. Of course, you have state space explosion, but what you then typically get is, well, there are algorithms that give you an exact number, but most of the algorithms that scale, they give you you can specify an epsilon, and then they compute for you a result that is guaranteed to be within an error of epsilon around the true result, which we of course don't know, and we are using a relative error criterion here. And of course, on the other hand of the spectrum is statistical model checking, where you don't build the state space, but you just sample some runs, you estimate the results, which is very nice in terms of memory usage, no explosion in the memory there. But of course, as mentioned, you have the problems of runtime explosion on rare events, and you can't really deal with non-determinism. But what's important for me here for this talk is that the typical guarantees are kind of variants of this probably approximately correct thing here, that you have your estimate that you compute, and then there is an error between that and the true result. And you just, before you do this analysis, you have a certain probability that the outcome will just be completely wrong, will differ for more than epsilon from the unknown true value, and you bound this with some confidence level. And you can do confidence intervals, you can do Okamoto bounds, whatever. There's different techniques to then instantiate kind of guarantees like this. And what's also interesting, and what also mentioned in a very recent previous talk here, that of course there's hybrid approaches. You could do learning with very weird things to represent your state space, like in deep learning. We had a tool that does truncation, so that can handle infinite state continuous time Markov chains. There's partial exploration tools, which is kind of the typical thing done in probabilistic planning. So where you try to only build a part of your state space, and then that suffices for you to get an epsilon bound, either that one or that one here. And so this was also then interesting to see how these tools perform in relationship to the two kind of extremal standard techniques that we would have. But I actually focused a lot on this on these error things, because they of course pose a certain challenge to setting up such a competition and to evaluating the results. So that's what I would like to quickly come to. Of course, now You want to run tools on selected benchmarks, and then the tools will produce a result, and you want to compare not really the result, you want to compare the performance of the tools. And of course, you can implement a very, very quick probabilistic model checker by just answering 0 to 1. That's the interval where the result is in constant time. But that's useless for, I mean, yeah, you would probably win the competition on performance, but your results are useless. So somehow we need to have a criterion that you must deliver results up to a certain precision. And what happens if you deliver a wrong result? Why would you even deliver a wrong result in this? And so let me give a brief overview of course, what can cause problems here. And the obvious one is that simply, well, you use an algorithm that's not correct. You could ask, why would you do this? But often you just don't know, right? So we had the sound value iteration algorithm, which I implemented from the CAF paper where it was in. And yeah, it worked very nicely until I ran it on the whole benchmark set. And then it gave a wrong result on one of the 79 models. And I then figured out with the authors, there's a tiny little bug in one of the helper methods. So yeah, if I had competed with that, I would have produced the wrong result with that implementation of the algorithm, because it was simply wrong. And of course, then I can mess up when implementing the correct algorithm. That's the usual case where you simply have a bug. And the question is, what do you do with this in the end? What do you do with a buggy tool? Maybe it gains performance because it has a little bug. And maybe that bug isn't even triggered by the benchmark. So then you have a buggy tool where the bug helps it get performance. That's not great, right? And the question is, are these acceptable? I would say no. What can you do about them? Well, you really need to get the big cannons to get rid of these. You need to do program verification. You kind of need to use our own technology, which is not always something that we like to do, apparently. But these are really, I mean, they are not specific to doing something with stochastic models, right? They are a problem in any kind of competition. So we can kind of look at what others have been doing. But if we come to more specific things, one big problem is that many people use algorithms that are sort of correct, but not really, in the sense that they will eventually converge to the correct result, but you don't really know when to stop. This was the famous example of value iteration, where you build the state space and then your solution is a fixed point, and you kind of, so here's the true value, and I'm plotting the value you actually compute, and here's the state. So for every state, you compute your probability to reach the goal. You start with an under approximation here at 0, and then you iteratively improve that up to a certain point, then you stop. But the problem is you never know when are you within epsilon, which is what we want. And of course, many tools implemented that, and we're quite happy with that for years. But in some sense, it's wrong, right? But it's fast. Well, there are solutions which are a bit slower, which amount to bounding this. So in some sense, this is solved, but still we have many tools to implement these kinds of algorithms. The question is, should we exclude them or not? Well, yeah. The other elephant in the room is that we typically implementing things with floating point arithmetic, which means you get rounding, you may get cancellation if you're not careful. And if we're being very strict here, you don't really know what you're getting as a result in the end. Because, I mean, I can produce you a model if you give me enough states that gives you any error just because of floating point rounding here. So you could try to do exact rational arithmetic, but that doesn't scale to big models. I've been working on safe rounding here, but that's very new. And so these are really problems that probabilistic model checking algorithms give us here. And well, this one is kind of easy to deal with. Don't use these stupid algorithms. This one is a bit more problematic, right? I mean, we kind of, if you're not allowed to do floating point things, that's a problem. Okay, so maybe we don't use probabilistic model checking because it has these bad things. Let's all do statistical model checking. But then, of course, by definition, you have this problem that randomly up to, let's say we use 95% confidence, 5% of the results are simply completely off. And somehow that's okay, right? And because that's coming from this PAC guarantee. And the question is, what do we do with this, right? This is unavoidable. It is quantifiable. But yeah, now you're evaluating these tools. And if somebody tricks a bit, I mean, if a tool uses, if we say everyone should use 95% confidence and the tool uses 90%, they're going to be a bit faster. So the real question is how to deal with these things in such a competition, which I think is the specific challenge we face when dealing with the stochastic things. So, well, what do we do? Well, one option, of course, to consider is what I call option N, and N stands for a nuclear here, which would be that simply if you submit a tool and you produce an incorrect result, then you are disqualified and we publicly shame the authors of this tool. Well, I don't know if we want to do this. This is what I think, for example, the satisfiability checking competition does, minus the shaming of the authors, that they simply say, if you say it's SAT, but it actually is unsat, I mean, nobody should be using your tool. So you must not do this. If we do this here, right, I mean, it has the obvious consequences. It means statistical model checking is out just because of the statistical error. It means no unsound algorithms. Now you could say maybe that's a good idea, but it also would kick out a lot of today's tools, at least. It also means no more floating point algorithms implementation, sorry, at all, because then I would put my model that gives you an arbitrary error due to rounding, and all the tools would be disqualified based on that. So all that remains is basically Storm and Prism using their exact engines, which can't really solve practical problems, and that's not really what we want. We could do a statistical test on the statistical model checkers, right? To, with some confidence, assure that they give the correct confidence, but then we really get a competition that uses a lot of computational resources. And all in all, this is not an option. I would hope that we all agree on that. So the question is, what can we do? And well, in our first iteration, so we had actually QComp, sorry, not 19, but 2019 as the first edition, where we treated this as a bit of, we don't really want to deal with this problem, and we trusted people to do the right thing, and we agreed on some epsilons, and we agreed on tools really trying to get that epsilon, and if you're a statistical tool, well, then you're allowed to have some errors, and we don't kick you out. But that wasn't really satisfying, right? Because then, I mean, in some sense, the probabilistic model checkers go to some effort to not have these errors. And now they're kind of competing with tools that are allowed to sometimes be wrong. So our option now for 2020 was simply to, well, very simple, very pragmatic, to say we just use different tracks where you have to provide different guarantees. And of course, they are matched to the guarantees that the algorithms can give. It's just tough luck if you have an algorithm that gives a different guarantee. So we had a track where your results must really be exactly correct. No epsilon here. You can do this, but you can't handle big models. We had a variant of this where we said, okay, maybe don't use rational arithmetic, but you can implement the same algorithm, but with floating point. In essence, this was a bit exploratory. We wanted to find out what happens if you do this, and what the practical results are. Then here comes the one that's for the probabilistic model checkers. Well, epsilon 10 to the -6, you must give us a relatively correct result. And there's the one for the statistical model checkers. And of course, we expected everyone who can solve this one to also participate in this track, and then to see what they can still do. And here we set the epsilon quite a lot higher, because otherwise you're getting into a kind of, well, not really rare event, but high precision setting where the statistical tools just cannot compete. We knew this from before. And we had a track where then all the unsound algorithms were allowed, where simply, well, you should do this bound, but you are allowed to sometimes be wrong, but just please do your best effort to get this result. And then we're simply reporting how in the competition report how often you failed on this. That's in essence what we had done in 2019 here. So this is not really a solution, well, not a direct solution to the problem. It's a pragmatic way around the problem. It expands the competition a bit, but it also, I think, in the end gave us some very interesting insights into the performance of the different tools. And here are the tools that participated. So we had 4 probabilistic model checkers in there. One was EPMC from Beijing originally. One's my tool here. We have PRISM, which I would think is the longest established tool, with Dave Parker competing with that. And we have the STORM people from Aachen. Well, where I would say STORM is the tool. Like if you write a paper on the new algorithm and you show that it works really well, wait 2 months and it will be in STORM. So they have it all. We had 2 statistical model checkers in there. I'm wondering, I would have had liked to get more, but these were the only entrants we had. So one is on dynamic, it's very specialized to dynamic fault trees and rare events. And the other one is my more generic statistical model check. It can do rare events and non-determinism, but we didn't use that in the competition because then you would need to configure this specifically for every benchmark, and the non-determinism engine doesn't give us guarantees, so that's not helpful. And we actually had 3 hybrid tools. So one's implementing probabilistic planning algorithms. We had the PET tool from Jan Kraczynski from Munich, which tries to do this partial exploration business, so explore the part of the state space that is relevant and ignore the stuff that gives you less than an epsilon error. And of course, trying to beat the state space explosion problem. And we had the stamina truncation tool from Utah in here. So these are the 9, if I didn't count wrong, entrants. And we have a little matrix in there of all the kinds of things they can do. So here we have all the input formats, and then you can see which ones of these they support. So you see that there's a bunch of tools that support the Jani format, except obviously PRISM, because, well, they are the established tool. They don't need to implement a new formalism, and these that had already settled on supporting the PRISM language before. Now, this is something that really is a problem if you want to set up a competition and every tool has its own input language. Then how do you even get your large set of benchmarks to work for these? How do you make sure that if you translate a benchmark from one language into the other, you're not already making some optimizations specific to the one tool that you have in the end? So we could just barely deal with this, I would say, by having all models available in Jani, and then these 3 tools could only compete on a subset of the models we selected, those in the PRISM format, and then we somehow made sure that there's a significant amount of PRISM format models in. But if we had the same situation with yet another format, things would get really difficult already, because then you're really fragmenting the whole competition. Yeah, and many tools came originally from like Great SPN or so, but then Storm provided a Jani translation of those. And here's the kind of formalisms and properties, so probabilistic reachability, expected rewards. I think this is time bounded here, a steady state, and so on that they support. Don't look at all the differences. You see that compared to 2019, the tools made steps. Some of these improvements really triggered by the previous competition, that here in the planning tool, they now expanded their support for I think to minimum probabilities or something like that, just because they wanted to be able to compete, which I think is a nice outcome of a competition, that we really push the tool development a little bit. And here's then which tools participated in the different tracks. So, well, Storm is the only one that did fully correct model checking. I'm wondering a bit why PRISM was not in there, because at least now they have this engine on exact arithmetic. I kind of hacked MCSTA to compete in the floating point track, one just by running value iteration until a fixed point and otherwise giving up, which provides some interesting results compared to the real exact but floating point implementation of Storm. We have the probabilistic model checkers in here, and then, as I said, these are statistical tools, and then everyone's in here. We also had this last one here where we said, okay, you get 10 minutes, now give us the best result you can do, and then we wanted to compare the epsilon that we got, but in the end, this turned out not to be useful because everyone terminated in less than 10 minutes on our benchmarks, or completely ran out of memory or time and couldn't do anything in 10 minutes. So there's somewhere there's this bound between, yes, you can do it, and then you can do it in less than 10 minutes, or, well, no tool can really do it, or you can't, at least you can't really do it, and then 10 minutes is, I mean, you don't care. So I think what you see here is a bit, of course, that we have this division on the generalists and the specialized tools, and then obviously the specialized tools, like for example, the DFT-RES, they only can handle very few of the benchmarks, but maybe then they're really good on these. And that's another challenge, to reflect this properly in your evaluation. And maybe you have a single winner, but then that's your generalist tool because they can solve most models. But still, of course, the specialist tools have an important contribution to the field. So you don't really want to make it look like they're useless when you're doing this competition. But that's also why we were friendly. And one issue, I fear that I will be running out of time. I apologize, but I hope I can do this a tiny little bit, is that, of course, especially older tools, they provide lots of different options and algorithms. And the question is, of course, which of these do you use to win the competition? And maybe some people really want to win, not just participate. And there's two ways that we could do. We could ask every tool to say every tool must run in its default configuration, like command line, tool name, model name, property, enter, and you go. Like a stupid first-time user would use the, well, not stupid, but an intelligent, but still not accustomed to the tool, first-time user would use the tool. So that's interesting. What does the tool do for a user who's not the developer of the tool? But you could also say, well, you should just, for every benchmark instance that we have, you should select the absolute best algorithm and configuration that your tool can do, because that showcases the abilities that you have in your tool, and that's what you're competing on. So I think both of these have a merit, and the question is, what do you do? Well, I think you can by now imagine what the approach is that we did in QComp, at least. We just did both. So you have a default configuration, and every tool was also asked to give a specific configuration if they wanted to spend some time on tuning their tool. And so default was, okay, per track, modeling, formalism, and property type. Tell us what you would recommend to people today. So it doesn't really have to be the actual defaults of the tool, because participants pointed out that some of their defaults are kind of historical, but they can't change them because people rely on it in other tools that use their tools. Well, now it turns out that this year we had a tool that really wanted to win, which was Storm. And what they did is that specifically, because we're doing this competition, well, I mean, that's what I'm saying, but well, they just implemented an automatic selection of their engine and some parameters based on some syntactic aspects of the benchmark. Now, why I'm saying they did it for the competition, well, I mean, they trained that thing. They learned a decision tree from the benchmarks, and we used the same benchmarks in 2019 and 2020. So, well, yeah, it just meant we had a problem, right? I mean, now this distinction is kind of pointless, because Storm is in its default configuration actually doing specific things. It's also a bit related to a question you should ask: are we comparing algorithms or are we comparing tools? And I think we're comparing tools. And then in some sense, this is what a good tool should do, because it makes life easier for the user. It's just that right now, it kind of violated one of the assumptions of the competition, that we had no tool. Doing this so specific and default made sense. Again, well, what did we do? We had a long discussion with them. In the end, we agreed that they get to compete as Storm with the automatic engine, but also with a static version of Storm that doesn't use that. And then we can even see what their automatic thing brings them. And now, I am sorry for running out of time, but now let's show some graphs to conclude this talk. What did we actually find in the end? Well, we selected, as I said, 100 benchmark instances, where this word instant means that it's a model. It's a set of parameters that may scale your model up or down, and it's one of the properties, well, like one probabilistic reachability query or so that you can do. So each of these is like one single task for a tool from our benchmark set. And we're showing in our competition report two kinds of plots. One of these are these quantile plots. And if you, for example, ever attended the SVComp presentations at TACAS, this is how they present their results. And here, this means that I'm very careful because they are very easy to misunderstand, these plots. So here, like this point here means that for storm, the 20th slowest instance took 6 seconds to complete. And then the 30th slowest instance took whatever here on a log scale is instances to complete. So these are not cumulative values, these are per instance, because we essentially took the results for storm, we sorted them by runtime, and then we plot them here. This also means that the benchmark instance causing this dot here for MCSTA may be a different one causing the same dot, because the 20-second fastest one for MCSTA may be different from the 20-second fastest one for storm. So there's lots of information hidden, but you can plot very nice plots here. But you always need to know what they really show to you. So it may well be that storm takes very long on this model on which MCSTA is very fast because it's over there. Good. So what we here see, this is the floating point correct track. And in essence, what I want you to look at is just to see how much the automatic selection of benchmark improved storm performance. So here, this is with default, this is with specific. So this means here, storm static is kind of hand tuned. And it turns out that the automatic selection here is pretty much as good as the hand tuned version. Here, it's slightly better. In other tracks, it was just slightly worse. So this was pretty powerful. Good. So here's the epsilon correct tools. That means the probabilistic model checkers and PET. And these are the plots we get. Here we had to kind of, this is showing only 43 of our 100 instances because they are the ones supported by all the tools. And since we have Prism in here, it means we only get Prism language models allowed here. But if you don't make this restriction, then in essence, not being able to support a model would look like a timeout over here, which is not the same thing, right? So that's the difficulty with these plots. And that's why we also do scatter plots. They are much more useful, right? I mean, here, this means that for this plot here, there was, I don't know what orange means anymore, but this means there was one instance where MCSTA took like, I don't know, 50 seconds, but the best of all the other tools just took 1 second. So this is kind of seeing how does this tool fare to the whole field of competitors. And anything above the line is where this tool here is the best of all tools. So ideally, you want lots of dots over here. And then you can see interesting things that, of course, here storm looks amazing. But then if you actually look at the scatter plot, you see that there's still a whole bunch of models where other tools are better, and this information is lost in these quantile plots. So I think this is the challenge of how do you even present the results of such a competition without overwhelming the reader, but also without hiding important information. So here's another one, statistical model checkers. If you look at this quantile plot, you see that modus, the statistical model check, it beats everyone until you get to kind of the rare event models. So, but this is only on DTMCs and CTMCs. This is if you put in all instances that we have. And suddenly it looks like modus is a total loser here. Well, that's just because it doesn't support the other ones. And it's pretty much not supporting, it's pretty much the same as a timeout, as I said. So it's more interesting to look at the scatter plots where here you see modes. Really, on the models it supports, it's really good to use statistical model checking, so for the DTMCs, CTMCs. Whereas if you have a more generalist tool, it doesn't win that often, but it supports a lot more models. So I think that's a lot more interesting. And I think quantile plots are really like statistics. You can, like at least the famous sayings about statistics, you can make it show whatever you want in the end. Good. With that, let's slowly come to the end here. This is the results of the track where everyone essentially was in. So that's the plot with all the instances and all the tools. But I personally find it doesn't show that much. I recommend you take our competition report and look at the scatter plots. We found out, as I said, the 10-minute version is useless. Now, if you look at these, who is the winner? I mean, we didn't want to crown a winner, but would you be able to tell? Now, of course, here you see that the blue line is always the lowest, right? So it always has the fastest solutions overall. And that's, well, no surprise, that's Storm. But you may also want to look at their scatter plot for Storm. And then you would see that, yeah, there's still a whole bunch of models in this area where other tools are better. So yeah, I'm not sure if I would call them the winner. They're pretty good. They have a lot of stuff, but there are tools for certain models that are better. To summarize, thanks for staying with me so far. We have these approaches, we have these challenges, some of them especially in this quantitative setting we're working in, where you don't really get exact results, and some other problems. We had this competition, which turned out to be relatively large in the end in the number of evaluations we took on a single machine, I should say. So we didn't have a big cluster to run things on, but still it worked in, I think, 1 or 2 weeks to complete all the things. These are the outcomes. There's a competition report, which was published at ISOLA, which I actually presented in person 2 weeks ago. That was very nice. It should have been in 2020. And yeah, that almost concludes. If I am allowed, I would do one slide of advertising. If you're working on the fringe of formal methods in software engineering, consider submitting here. But maybe much more interesting to us is that I'm organizing with Dirk Bayer a workshop on reproducibility and replication of research. So, I mean, it often happens that you need to implement somebody else's algorithm just to compare to it or something like this. And usually you can't really publish. There's interesting stories, interesting experiences, but nobody knows about them. And we want to give a venue to talk about these and to get them published. So take a look at our website if you're interested in that. And with that, I'm really finished and would like to take some questions.
Thank you. Thank you really very much. Okay, we absolutely don't have time for questions, but since we are at the end, I mean, we may also don't mind because people can just leave and go and eat. But we have an okay. Let's see if we have questions that somebody want to pose now.
Should I pop in? I'm just raising the hand.
Just put on your mic.
Hello. So I love the nuclear option, but another question was with the dimension in the end, actually. Are we comparing tools or algorithms? And yes, we are comparing tools. This is a tool competition, friendly tool competition. Now, was there any analysis across tool of algorithms that perform better compared to others? That really maybe...
No, so we explicitly didn't do this. Some of these things you can, of course, see with the specialized tools, where like MFPL uses the LRTDP algorithm, and you see how that fares compared to the whole field of competitors. But then you have someone like Storm, who for different models, I mean, for DTMCs, they use a different algorithm than for MDPs. So it's not directly comparable. You see some of these things, and I think it gives a bit of a trigger to look into that. I actually have a master's student now who wants to look into this very problem, but it's not a direct outcome of the competition. And it's also a bit, I think it's interesting, but of course it's not the goal of a tool, not necessarily to give you a certain algorithm, right? But as I said, this is a bit of a decision you need to make of what you want to evaluate. Otherwise, it's kind of you're evaluating how efficiently people are able to implement a certain algorithm, right? Is that interesting? I don't know. Maybe yes, or well, no, that's all I can say to that.
Yeah, thank you.
Okay, so I think I don't see any other questions. So
yeah, can I raise my hand? I would of course have the question of, like, we've seen lots of beautiful tools today. Are we going to see any of these in the next QComp Next, no matter when it happens?
I was exactly saying this. Okay, let me tell two quick story. We have been participating with CritSPN in the knowledge sharing competition on PatriotNet. It's a lot of work. So it's difficult to stay in two competitions unless you are a large group like Aachen. And so it's a bit complicated. It was only a matter of time and of work. But one of the reasons why I invited you to give this talk is exactly because I think that we should compare more. We should cross-fertilization among communities. And one suggestion is that worked quite well for PetriNets is that once we will go in presence, is to have meetings for organizing the next competition, where a researcher can actually, describe what they would like the next competition to be, what they found, etc. Doing this by email doesn't work. Try to avoid it. We have spent so much time reading emails that we have lost. So either in a meeting, physical or whatever, WebEx, whatever. But it's important that we actually share so that we actually make a comparison. For example, what can I do if I have a QE network tool in this competition? Can I do something? And sometimes it's easier to meet and just, to try to find an agreement on things that could be done. And I think this is important. If this is one of the reasons, but there are other people, maybe somebody didn't know about the competition. Let's say somebody didn't know about the competition.
So we're currently thinking for the next version of the competition not to do it. I mean, we definitely don't want to do it every year just because it's so much work, also for the organizers and for the PhD students and everyone. And the next one will probably not be the same setup, but be more looking into what new areas do we have? Like we have LTL, we have games, we have multi-objective. And I could imagine if there's interest that we have a category for, okay, what's actually going on in performance models, PetriNets, queuing, whatever is of interest there and related. So if somebody is interested in kind of bringing that perspective, then please just shoot me an email or come to Twente and be in my office if you want to do it physically.
Yes, I think we have Enrico here who is part of a steering committee. We have 1 or 2 people in the steering committee of CAST, which could also be a good venue where to start discussing this topic.
Yeah.
Okay. Well, I think we can stop now. I really want to thank everybody. To let you know that the afternoon program for teaching performance is very interesting and very much related to what we have done. One last thank to the presenter, to the authors, and especially to the general chair, Danilo Ardagna, that bear with us all the delay that we had in our organization.
Actually, it's me that to thank you because the program was very, very nice. I really enjoyed the talks today. I think very interesting and really they are a value for the conference. And also, I mean, of course, I bring you my thanks from Eugenia. For her, it's a bit early in the morning, but slightly early, but definitely I really enjoyed it. So I mean, what matters at the end is the quality, right? So I think we reached a very, very nice results today, and hope to see you later at TPAX really, and to continue this discussion together today. There will be more room, we hope, for also discussion, open discussion.